something that we often run into if you're looking at maybe sculpture or maybe tiling on the floor. And on the other hand, there's actually a rich mathematical theory of symmetry. And so what I want to discuss tonight is a few ways in which some questions that actually come out of certain artwork of Escher, mostly, which have certain symmetrical features and give rise to some questions which are not obvious how to answer, but that the mathematical theory of symmetry can be used to explain what's going on and give some indication of some of the unexpected applications that the same ideas have. So to get started, we have this quote from Hermann Weyl, who was one of the greatest mathematicians of the first half of the 20th century. And he sort of observed that on the one hand, in art and nature, we see a lot of examples of symmetry, but that in fact, this is a very rich mathematical subject. And if you want to convince somebody of the usefulness of mathematical ideas in unexpected places, it's hard to do better than to talk about symmetry. So the first thing I'm going to do is briefly describe in a somewhat precise form what I really mean by symmetry. And I'll mostly then be focusing on how we can use some ideas around symmetry to understand, these two works. So this is Escher's circle limit 1. And you can see if you look here, you have some black birds and white birds arranged in this circular pattern. And then they're going off to the boundary, shrinking in some slightly complicated way. And we want to ask, what is the exact rule that generates this pattern? And on the other hand here, in print gallery, you have a picture of a guy standing in an art gallery. And in the painting, there's the boat, and then these houses, and then there's a veranda. And then underneath that, well, that goes into a building, which is the one that the guy is in. So it kind of wraps around back to itself. And Escher couldn't quite figure out what to do in the middle, so he just put his signature there. And so we'd like to understand, is it meaningful to decide what actually goes in the center? And it turns out that the same mathematical ideas that will explain how to actually fill in the hole are used all the time when you use a smart card or any kind of secure internet communication. If you want to set up a secure link with somebody that you have not had prior contact with, if you think about it seriously, it's not at all obvious how you can possibly do that. But there's a beautiful mathematical theory that makes this possible, and it's the same mathematics of elliptic curves that underlies filling in this hole. So we'll get to that a bit later. So first of all, roughly what is symmetry? So here we have several examples. So this is a picture I took at the back of the Taj Mahal, and you have this very simple tiling pattern on the floor. This is the circle limit that I briefly described before, and then we have our Rubik's Cube. And these are each going to illustrate the following basic principle. So symmetry, when we speak about an object having symmetry, the idea is that something is built out of parts. There might be these black birds and white birds, or certain shapes on the floor, or these little cubes building up the Rubik's Cube with some color. And we want to talk about rearranging the parts so that some specific properties are preserved under the transformation. These properties could be distance, if we think about rotating this by 120 degrees, could be angles or perhaps colors. And so just to give some examples, if we look at the back of the Taj Mahal, we can imagine taking this tiling pattern and translating it a certain amount up, down, left, right, or possibly reflecting it along certain lines, and then it would come back onto itself. At the same time, for the Rubik's Cube, if you take one of these faces and you rotate it by 90 degrees, the geometric object is preserved. Of course, the pieces on one side have moved around, but the way they sit in relation to each other is the same, although admittedly not the same as how they sit in relation to the other pieces of the cube. Nonetheless, there's a lot of symmetry underlying all three of these, and it can actually help us to understand what's really going on in each case. Now, one interesting thing that you can do when you have ways of rearranging something to preserve some properties is, well, if you have two different rearrangements, you can apply one and then apply the other. So you can compose symmetries upon each other, and this can give rise to interesting new ones. So for a familiar example, so this girl is in a room with a mirror on the wall, and then there's a mirror behind her, and you may have, of course, seen this in the bathroom sometimes. You have two opposing mirrors. You have these reflections within reflections. So what she sees of herself here is a reflection, but then it reflects off the back mirror, and then there's a reflection of a reflection, which is actually a translated copy of the girl, a distance twice as far as the gap between the two mirrors. And so if you compose two different reflections through two different mirrors, you actually get a translation. Okay? So one can do this a lot with symmetries. And one interesting thing, aside from the fact that, of course, anything you can do, you can also undo, is the order in which you compose symmetries can make a tremendous difference. So, for example, if you think about the motions of a Rubik's Cube, twisting the different faces by 90 degrees, if you try to follow a recipe to solve Rubik's Cube, well, of course, if you do two moves in the wrong order, good luck. Okay? So the order in which you compose symmetries with each other can have a big effect on the net result of that composition. And in fact, group theory is a huge subject in mathematics, which is exactly concerned with understanding, among other things, how you can work with symmetries and understand the effect of order of composition. And all patterns that are involved in solving Rubik's Cube are in fact completely explained by group theory. But in a completely different direction, there are situations, and we'll come across one a little bit later, in which you have symmetries for which the order of composition does not matter, that if you compose one upon the other in either order, you get the same net result. And those situations, in fact, govern the mathematics behind smart cards. And the reason why the security method works relies crucially on the fact that in those situations, the symmetries are so special that the order in which you compose them actually makes no difference. Now, having said these generalities, let's now come to Escher. So as you may know, he was this great Dutch artist. He didn't have any formal training in mathematics, but he had tremendous geometric insight. And one thing that he had initially done in the early part of his career was he made very interesting infinite tilings of the plane. So you can cover the plane in repeating patterns of triangles and squares and hexagons, but he came up with much more interesting shapes. So you have this guy, and you have three different colored versions: the all-white version, the one with somewhat darker hat and vest, and the one with an intermediate color. And he fit them together in a certain way that he could then infinitely replicate in all directions in the plane. But he wondered whether it might be possible to do this kind of infinite repetition within a bounded region. Now, obviously, you can't do that if the pieces maintain a fixed size, but he wondered if there's a way of shrinking the size that somehow maintained the symmetry and enabled it all to fit within a bounded space. But he really had no idea how to do this. But he was in contact with a Canadian mathematician, Donald Coxeter, and one day Coxeter sent him this interesting picture. And this is called the Poincare disk. We'll see the significance of this a little bit later. And the thing I just want to point out is that in this picture, so we have a bunch of these circular arcs, the significance of which we'll see later. And in the middle, we have a kind of hexagon, although the sides are a little bit warped. And each of these hexagons is broken up into alternating 6 white and 6 black triangles. And off of each side, you have another hexagon, although admittedly it has 6 sides, although obviously it's not as nice as the central one. And after Coxeter sent him this picture, Escher got the idea of trying to line up blackbirds and whitebirds along these hexagons. But the problem was that he wanted to make this as a woodcut, which means he had to figure out how to actually construct this pattern on an actual piece of paper, or rather on a piece of wood. And he was quite confused as to what to do. So, well, he thought about it for a while, and he realized that the initial big arcs that made the central hexagon he could make by placing 6 circles of the same size at appropriately determined points. And, well, then it got a little bit complicated and more complicated. Okay, and then, so he got stuck. So he figured out different tricks by which he himself could make certain layers of this pattern of circular arcs, but after a few stages, he couldn't figure it out. He needed to go a few more down to really make a good picture. So he got totally stuck. And he asked Coxeter if he could give him some advice about what is the rule that's really governing this interesting pattern. And so Coxeter sent a very brief reply. He just drew this mysterious line segment and a little circle and didn't say anything more. So Escher was not very pleased with this, so he was quite frustrated. And so what I'd like to briefly explain is, I don't actually know how Escher figured it out himself, but mathematically, what is the actual rule that's governing this pattern, and in what sense is it truly symmetric? Because certainly these hexagons, the central one and the ones off of it, from our point of view, they don't really look the same at all. So in what sense is there really symmetry among those hexagons? And to explain this, I'm going to first look at a toy analog going back to the Taj Mahal. So this is another picture that I took in which we have the familiar hexagonal tiling pattern in the plane. And if we think about hexagons, on the one hand, there are 6 basic symmetries. You have 3 pairs of lines joining opposite corners, 3 pairs joining midpoints of opposite sides, and you can reflect the hexagon through any of these, and you get back the same hexagon. But notice that in here, if you choose the line, the blue lines, and you extend them, they go through the edge of an adjacent hexagon. So rather than flipping a hexagon around itself, we can instead think about the whole diagram reflecting this along an edge. And so that's the point of view I want to take, which is if we think about one hexagon and you reflect it across any of its edges, you get a new hexagon. And as you keep reflecting across edges, you get more and more hexagons. They never repeat. And in this way, you generate this entire tiling pattern. And I claim that the circle limit picture is actually a manifestation in non-Euclidean geometry of exactly this picture in the familiar plane. So what's the relationship? So first of all, we see here that indeed what Escher had done was lined up his blackbirds and whitebirds according to this pattern. But the question is, mathematically, what is really a symmetry that's generating all of these pieces from this one central big hexagon, making these smaller hexagons? So as I said, Escher knew how to make the central one, but then what do you really do to obtain the rest? And in what sense is this really a symmetry? Because it certainly looks like it distorted the shape tremendously. So now we're going to have to make a small excursion into non-Euclidean geometry to see how this is really a symmetric situation. And so to do that, we're going to first recall a very familiar fact, that you can't make a map of the surface of a ball accurately on a piece of paper in such a way that expresses both distances and angles in a faithful manner. Now, in a school textbook, you often see this standard Mercator projection, and this has the feature that it actually faithfully represents angles, which is really useful if you want to do navigation. On the other hand, as is well known, it massively distorts area ratios. So it makes Greenland look about the same size or bigger than Africa, whereas in fact it's much smaller. It makes Antarctica look truly gigantic. So there's a lot of area distortion, but the angles are preserved. This Lambert projection has the opposite feature. It actually respects area ratios, but it massively distorts angles, therefore is quite useless for navigation, and you've probably never seen it before. Okay. But nonetheless, those maps illustrate the idea that you can have the geometry of the surface of a ball and try to put it on a flat piece of paper, and you can express things, but there is some distortion of the surface geometry on the flat piece of paper. And there's another manifestation of this that we all encounter when we go on airplanes. So on the surface of a ball, if you take 2 points and you want to know the shortest path between them, you draw an equator, a great circle, that passes through those points. So if you're trying to travel by plane, you travel along these great circles, but under the Mercator projection, like from San Francisco to anywhere else, those nice circles projected turn into these very warped paths. So in a flat plane, the shortest distance between 2 points is a straight line, but from the geometry of the surface of a ball, it's actually this path. Okay, so the curved surface projected on a plane, the geometric straight line, so to speak, the shortest distance paths, turn into these very warped-looking things. Well, there's another kind of curved surface called a hyperboloid. It's not a sphere. And the geometry of that can also be put on a flat piece of paper, in fact, in a disk. So it's not the Lambert projection that we saw here. Okay, this comes from a different kind of curved geometry. But the hyperboloid, when you put it into a disk, it actually gives you the geometry of the Poincare disk. And if you take shortest distance paths in the hyperboloid, the analogs of great circles, well, what are the analogs of these plane trajectories? Well, those are exactly the arcs in the circle limit picture. So these paths in the geometry of the Poincare disk are in fact length minimizing from the hyperboloid surface into here. And the important point is that once you have a notion of distance, there's a well-defined way of generating a notion of reflection. In usual geometry, it gives you standard reflections. In hyperbolic geometry, it gives you reflections across these funny lines. And a hyperbolic reflection applied to this central hexagon actually reproduces all of these others. So from the viewpoint of hyperbolic geometry, these hexagons are in fact all exactly the same shape, and they're all generated by a reflection process, okay? And in particular, it looks like there's a finite distance from here to here, but in hyperbolic geometry, this is actually infinite distance. And so this picture is really the hyperbolic analog of the familiar hexagonal tiling of the plane. So there's a tremendous amount of symmetry in here if you see it from the right point of view. Now, let me show you one amusing feature of this, which is in usual flat geometry, you can cover the plane in triangles and squares and also in hexagons, but you can't do it with a seven-sided polygon, okay? However, in hyperbolic geometry, well, check this out, okay? So we'll see 1, 2, 3, 4, 5, 6, 7. So there's a seven-sided polygon here, and if you apply hyperbolic reflections, in fact, it perfectly tiles the Poincare disk, okay? So it's really quite remarkable. So hyperbolic geometry is a really beautiful subject, but it has very different features from usual Euclidean geometry.
Is that fractalesque at all?
Not at all, no. So that's the story of the circle limit. Now the print gallery is a quite different feature. This also will have reflections hiding in it, but they're going to use a very different kind of geometry related to what are called elliptic curves. So here again is the basic picture, and we want to understand what's going on. How do you fill in the hole? So there was a mathematician at Berkeley named Hendrik Lenstra who was on an airline once, saw this picture in a magazine, and he wondered to himself, well, gee, there's some spirally thing going on here. Can I continue the symmetry into the center in some systematic way? And he didn't initially know how to do this. Well, other people had wondered the same thing. So there's this book called Gödel, Escher, Bach by Douglas Hofstadter, in which he pontificates in some meaningless way about, what's going on? Oh, it's totally impossible. There's some mumbo jumbo about how, no, it's just impossible. You can't possibly fill the hole for some reason that doesn't make any sense. So it's just complete rubbish. So in fact, Lenstra realized that using the mathematics of what are called elliptic curves, which is a different kind of geometry, you can generate reflection patterns that exactly achieve the result of filling in the center of the hole. And in fact, those mathematical ideas were introduced by John Tate, who's a mathematician at Harvard, in 1959. And the basic idea in Euclidean geometry is an analog of the following. So you've all seen examples of a picture reflected into itself and into itself and into itself on forever. And what we want to do is, in a kind of curved geometry, replicate this kind of picture. So Lenstra was able to realize that using the mathematics of elliptic curves, which is different from hyperbolic geometry, he could actually generate reflection patterns that he could then use to fill in the hole. And when he did this on a computer, he and his assistant, they discovered something quite remarkable. So Escher did this all just by his geometric intuition, just out of his own artistic skill. But here's the exact mathematical version. Okay? And it's, all right, now I want to show you a movie which actually fills in the hole. Okay, so, sorry, my computer is stalling. So they generated a computer screen, a little short video, which, there we go. Okay, so now, you go here. Just give me a second. Oop. And full screen. Okay, you see that? All right, so now we're going to go on a little excursion. So, you look very carefully in the center, and eventually you see, oh, look, there's the guy. Oh, okay. All right, and the thing is, of course, it's actually an infinitely repeating reflection pattern, and you can, if you go to the Lenstra's website, and they have this video, it's mesmerizing, and you can change the parameters of the elliptic curve and get other kinds of things. So it's really kind of cool. Yeah. So it's actually, as I said, it's really incredible that Escher didn't know anything about elliptic curves, and he was able to somehow come up with this kind of yeah, pretty neat. Let's just one more, and there it is. Okay, cool. All right, and so just the final. Oops, sorry, the final slide. And okay, so well, I'll just show it here. So if you, what happens? The pinwheel of death. Okay. Anyway, so I was just going to show you one final slide. Here we go. So there are actually many, many, many examples in mathematics of ideas in symmetry that were introduced, and maybe like 100 years later, they turned out to be useful. Okay? So ordinarily, we can't tell what ideas for math will be useful at a given time, but there are actually lots of them. Okay? And anyway, so I'll end there.